this will be the equation that we have. This will be the equation that we have. Okay? Right, from this to this. Any question? From this to this. The reason that we can remove the ZA minus ZL because it's in the denominator. So, so the denominator is both of the equation has that. So of course, if we divide it, then it will be gone. And ZA is often it has a ZA plan, so it will be in the denominator, so it will be gone as well. Okay. So and after you divide that, then this is what remains. Okay. Okay. So. And then it's still, well, it looks very similar to the collinearity condition equation, but not entirely the same. So what's not the same is here. So originally, what we have for the collinearity condition equation is YA equals to, or just Y equals to minus F, right? And these two. Okay, so where can we get this minus F? As you can see, if we move the ZA to the right hand side, then supposedly here should be ZA, right? Supposedly here should be ZA. And ZA will become minus F. Why? Because because the origin for the small x, y, z is at the perspective center. Right? It's at the perspective center. So, like I said, and also the z-axis direction is pointing at the opposite direction of the vertical line, so which is towarding the sky. Okay, so which means that if our image plane is over here, here is the negative value for the z. Here, this direction is the negative value for the z. And because we also know that the image plane is perpendicular to this z-axis, so which means that all the image plane coordinates has the same z coordinates value, which is the focal length. Because the ZA is over here, and image plane, the distance from image plane to the perspective center, that is the focal length. So that is the focal length. And so in this case, ZA equals to minus F. If F focal length is positive, then of course ZA should be negative. So it will be negative F. Okay. So let's replace ZA with the negative F, and voila, that's what you have. Okay, so yeah, so basically what I'm trying to say over there is this. So divide the first equation by the third one, second equation by the third one, and then let the ZA equals to minus F. Then you have the collinearity condition equation. Okay, that's okay. Hopefully you guys can understand that. Any question? Any question to now? Right. So earlier, I believe earlier in this semester, I talked about when we talk about the coordinate transformation functions, we were saying, okay, so we will introduce conformal transformation, we introduce affine transformation, and also 2D projective transformation. So those are the transformation between two-dimensional coordinate system with another two-dimensional coordinate system. So, and at that time, actually, I also mentioned, the coordinate condition equation is also a coordinate transformation function. So, but it looks very strange because Y is a two-dimensional image plane, the X and Y. It seems like it's a two-dimensional coordinate system, and the x, y, z, that's a three-dimensional coordinate system. It looks like, okay, so it's a two-dimensional coordinate system to the three-dimensional coordinate system relationship. But as you can see, this coordinate transformation function is actually a three-dimensional to three-dimensional coordinate transformation function. So your image coordinate system is actually a three-dimensional coordinate system by using perspective center as the origin, and here is the z-axis, right? But because all the image plane points, they have the same z, they have the same value, and that value is the focal length. So this focal length is actually another axis. So it's the three-dimensional axis to the three-dimensional axis, three-dimensional coordinate system to the three-dimensional coordinate system transformation function. Okay, yeah, that's the case. Okay, any question? Well, if no question, then let's extend it a little bit more. All right, so this is a question for you guys. Earlier we talked about the two-dimensional 2D projection transformation. 2D projection, which is the 8-parameter transformation function, and the purpose of that is to describe the relationship between two planes that has a certain perspective transformation, perspective projection transformation. So, and that at that time, I also told you guys, say this equation is actually a simplification from the collinearity condition equation, because it looks very similar to the collinearity condition equation. So, how does it transform? How can we derive the two-dimensional, the 2D projective transformation? Because let me ask you one question. For the 2D projective transformation, how many parameters that we have? We have 8 parameters, right? We have 8. A1, B1, C1, A2, B2, C2, and A3, B3. So we have 8 parameters over there. For the collinearity condition equation, how many coefficients that we have? How many coefficients that we have? 6. We have the EOPs, right? So we have the X, Y, Z, X, Y, Z, 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 and also omega, phi, gamma. And in this case, like I said earlier, 2D projective transformation is a simplification from the collinearity condition equation. Then, if it's a simplification, why the parameters from 6 to 8? More coefficient means more complicated. Why? I said it's a simpler version of collinearity condition equation. Okay. It's your turn to speak. I like this part. Any thoughts? Any thoughts? Alright, one hint. the coordinate condition equation really only has 6 parameters. And of course, the answer is not. So how many parameters that the coordinate condition equation has? Okay, so you guys are discussing like quite intensively. Alright, so any thoughts? Any thoughts?
Omega phi kappa has sine cosine.
What? Omega phi kappa has what?
Sine and cosine.
Sine, cosine.
So it should times 2.
Oh, okay. But eventually there's still omega phi kappa, right?
Yeah.
Still omega phi kappa. The same idea goes to, for example, like you have the azimuth and then a distance. You can calculate the delta x and delta y, but eventually you still have d and the distance and also omega distance and also your azimuth, the phi. So you still have two. Doesn't matter which like sine or cosine that you apply. Yeah.
The shift.
The shift? The shift of what? What shift? What x and y? Try. You may be correct. No? You may be correct. So you just need to say it. Alright, so Kunio mentioned that it's some sort of shift. What are the shift? What is the shift that we have? Where do we have shift? Where do we have shift? Eugene? No? So,
I have no idea.
I
so
thought you
far.
were trying to raise you. We have a shift, right? We have a shift. Somewhere. We have a shift. We talk about the shift. What is the shift that we didn't include? We didn't write it, actually. Really?
Scale.
What do you mean by scale?
So the scale is
You explain first. Why should I do this right or not? You may also correct. You may also correct. Depends on your answer.
From x plus y plus z plus 2 xy.
Yeah.
The scale.
The scale
The,
changes. Okay.
yeah, and the x1, y1, z1
Uh-huh.
with the x2, y2, z2.
Okay.
Yeah. The scale is then that is same, so they use the the other parameter to change the scale.
Yeah, the parameter. So you mean they add more parameter to change the scale? But like I said, alright. So your answer is the 2D projective transformation. It has more parameters because you will add additional parameter to change the scale. That's what you're answering. All right. All right. That's not correct over there. What I'm trying to say is, first of all, the coordinate condition equation, it doesn't only have 6 parameters. Right? It doesn't only have that, and so we have more. We actually have more coefficients or more parameters than 8. We have more than 8 parameters, and we simplify this coordinate condition equation to only have 8 parameters. Okay. So Kunio was actually onto something. Shift. What exactly is a shift? Okay, tell me in Chinese, in Mandarin.
就我是想影像的坐标跟实际的坐标不一样，它可能会有些变，就是它起始点。
什么是起始点？什么起始点？
就
原点的偏移，原点的偏移是什么鬼？好，讲中文太粗俗了，糟糕。是什么东西？
就因为一般的坐标系统，它会有个参考地方，但是你相机
好，我再问很单纯，你影像上面的原点的偏移是什么？我们讲过这种。